We rely on a system that feels invisible, but it's actually made of steel and wire. Every time you send a text, your phone is talking to a massive multi-million-dollar tower just like this one. But that reliance is exactly what makes the system fragile. If those centralized towers lose power during a grid blackout, or if you simply travel far enough away from one, your phone becomes a very expensive paperweight. It doesn't even take a power outage to break the connection. If you put thousands of people in a dense area, like a stadium or a festival, the sheer volume of devices trying to reach one single tower causes a bottleneck. The hardware works perfectly, but the network is paralyzed. So long as our ability to talk to each other relies on renting access from massive telecom monopolies, we remain dependent on their hardware holding up against both physical failures and digital congestion. There is an alternative. A completely off-grid, subscription-free way to communicate that requires absolutely no cell towers or internet. It's a project called Meshtastic. It pairs open-source software with cheap off-the-shelf radio components to create a localized public utility. The structural logic shifts. Instead of a phone that passively connects to a distant, fixed tower, your device becomes a physical part of the infrastructure. But that raises an obvious question. How can a $40 piece of plastic and a tiny wire antenna compete with the reach of a commercial cell network? These little nodes transmit text using the 900 MHz radio band. If you look at the radio spectrum, that frequency sits right between the AM and FM dial in your car and the Wi-Fi router in your house. The challenge with using these low-power signals is a concept called attenuation. When a 900 MHz radio wave hits a solid mass, like a concrete building, a hill, or even a dense cluster of trees, the signal is physically absorbed and weakened. To see what these devices are truly capable of, experimenters will occasionally test them from the inside of a commercial airplane, eliminating all ground-level obstacles. Up there, without any concrete or rock to absorb the signal, the true power of the hardware becomes clear. A single battery-powered node can successfully deliver a text message to another device over 100 miles away. The hardware has the reach. Since we live on the ground, surrounded by trees and buildings, we can't rely on a single device to push through all that matter. We need a different architecture. Imagine 3 hikers scattered across a mountain range. 2 massive, jagged peaks sit between them. If they try to radio each other directly, the rock will instantly absorb the signal. But if we place an unmanned Meshtastic device, called a repeater, at the highest point of each mountain, the physics of the environment shift in our favor. When the first hiker sends a text, the nearest repeater catches the signal and instantly rebroadcasts it. The data hops right over the first peak, strikes the second repeater, and bounces straight down to the furthest hiker. This happens in fractions of a second. There is no human intervention, no internet connection routing the data, and no connection to the electrical grid. This is what engineers call a mesh topology. Instead of letting the environment block the signal, the system uses strategic high points to catch and throw the data over the obstacles, expanding the network's reach with every new node. To actually see this invisible data in the air, you have to use a tool called a software-defined radio. By tuning into the right frequency, you can watch these text packets appear as tiny, cascading blips of data on a waterfall display. Looking at the data flow reveals a trade-off. You can achieve significant range on very little battery power, but the cost is a severe limit on your bandwidth. You cannot load a website, send a photo, or drop a voice note. The system is strictly engineered for short text bursts, capping out at around 200 characters per message. Yet even on a completely public airwave, those texts remain secure. Every direct message is locked behind heavy AES 256 encryption. To anyone else scanning the frequency, your text looks like nothing more than random noise. Ultimately, it is a stripped-down, text-only pipeline. But those precise limitations are exactly what allow the hardware to push signals so far and stay running for days on a single charge. When you take that low bandwidth protocol and scale it up from 3 hikers to hundreds of users, the geometry of the network becomes increasingly dense. You don't have to guess what this looks like. Groups like the Austin Mesh have already proven that this hardware can weave together a reliable communication web across an entire metropolitan area. The backbone of that citywide web is built by volunteers, mounting solar-powered repeaters to high rooftops and water towers. Because those high-altitude nodes generate their own power and talk directly to each other, the entire Texas power grid could collapse, and the mesh would simply continue routing messages. The project demonstrates that massive communication infrastructure can be assembled and maintained entirely outside of telecom monopolies or state control. We spend our lives paying monthly fees to rent space on fragile towers that fail right when we need them most. Meshtastic offers a model where communities actually own the physical hardware of their connection. There was no corporate mandate behind this. It was built piece by open-source coders and radio enthusiasts experimenting with cheap antennas. It shows us that with the right protocol, you don't need a central authority to maintain a resilient network. The community can build it themselves.